All right, thank you very much. I'm very happy to be here. Very happy for the invitation. You can hear me all right, yeah? Okay, I know it's the perfect time for a postprandial nap, but I will try to be loud and interesting, or at least one of those two things. So I'm going to talk about going back to some stuff that we talked about on Wednesday, changing topics a little bit. Dark matter in main sequence-ish stars. So I just want to acknowledge this is work with a lot of different people from, fantastic people from around the world, and some ongoing work as well that I'll talk about. So just to remind ourselves, what is a main sequence star? This is our standard temperature luminosity diagram, the HR diagram. I'm talking about these guys here, the ones that are supported by boring thermal pressure. Burning hydrogen, and the ish here means that I will talk about some red giant stuff as I go. So I'm being boring in that I'm talking about the main sequence, and I'm going to be boring in that this is a map of sort of theories of dark matter. I'm going to stay fairly close to safe shores, the sort of classical WIMP asymmetric dark matter region here, and I won't be venturing over where there are dragons in the modified gravity region. So as a little reminder, we heard much earlier in the week, so WIMPs, weakly interacting massive particles, those I kind of think of as sort of hundreds-ish to thousands or tens to thousands of GeV mass particles that are produced thermally in the early universe via some kind of freeze-out mechanism. And asymmetric dark matter, which we'll talk about as well, so WIMPs are produced via annihilation of the dark matter in the plasma to other stuff. And you can think of a sort of cousin of this, of asymmetric dark matter that can also be annihilating, where you start with some initial asymmetry, and you can even try to link it with the baryon asymmetry between matter and antimatter. And if you sort of naively do that calculation, if you have a sort of 1 to 5 abundance of mass abundance of dark matter, and you want a number abundance of baryons to dark matter, that gives you a rough mass scale of maybe 5 GeV for your dark matter particle. Of course, as we saw with, I think it was Laura's talk, you can get theories that have couplings and masses that are kind of all over the map. But that's sort of some of the framing that I'm going to use, just because this number turns out to be the optimal way of messing up a star, which is a fun thing to do. So just to start with, direct detection of dark matter. So this is sort of one of the most advanced, just because of history, ways in which we've been searching for particle dark matter. And the idea there is you take a large quantity of some nucleus, or some element, you stick it very deep underground in a lab, isolate it from any kind of cosmic rays, so that if a dark matter particle comes in, it can hit one of your nuclei, cause some recoil, and then you'll get some scintillation or some phonons or something that you can go and measure. And the advantage of putting it very deep, isolated in a lab is that if you see one of these events, you're pretty certain it's not cosmogenic or radiogenic. So this sort of experiment is most sensitive to heavy, fast particles because those are the things that are going to give you the largest energy recoil and therefore the most visible signal. And just to remind you, so we often plot this sort of exclusion or detection, if we're being optimistic, in this sort of dark matter nucleon interaction cross-section on one axis and dark matter mass on the other axis. And effectively, we're limited, our sensitivity is limited from the bottom just by the size of your detector, because the larger your detector, the more flux there is to possibly interact with your detector and produce a signal. And the sensitivity at the low mass side is limited by the fastest particles in the dark matter halo being able to produce a recoil with enough energy to actually see. So you need so the lower your mass, the faster that particle needs to be, and we can't go any faster than the local escape velocity because that dark matter is gone. It's not here. It's not going to produce a signal. So if we're interested in sort of the low-ish mass, high sensitivity regime, we need a big detector, and we need a target that's preferably lowish mass, like, I don't know, a proton. So what's, this is what it looks like in reality. So what's big and mostly protons? The sun. So I'm going to try to convince you that the sun is a direct detection experiment. It's hard to actually read out. It's not very shielded. But the idea here is that the sun is going through the dark matter halo of the Milky Way, and your particles come in, and they can scatter with nuclei in the sun, scatter below the local escape velocity, they're gravitationally bound, and now we can try to figure out what it will do. Now, I know a lot of talks have discussed things like what this will do in a pulsar and various types of neutron stars. But I'm going to ask what happens first in the sun and then other similar stars when we have this capture of WIMP-ish dark matter in the star. Now, our sun is 10 to the 30 kilograms, which is larger than the LZ experiment. It's mostly hydrogen. There's some helium, so better kinematically matched for sort of GeV-ish dark matter. So that's a good target region. But there's also a lot, 2% of 10 to the 30 kilograms is still a lot of kilograms. And so if you're looking for heavier dark matter, it's also good. And there is, in some couplings between dark matter and nucleons, an A squared atomic mass unit squared enhancement. So that makes that means that these elements can come to dominate in some models. So what are the actual ways of seeing the dark matter accumulated in the sun? So the classic one that we've been sort of thinking about for the last couple of decades is you accumulate dark matter in the core, and if it's something like a WIMP, it can self-annihilate. And if it does this, it can produce stuff. Any standard model stuff that's sort of a muon or heavier is guaranteed to give you some neutrinos. And since the sun is nearby, we have very large neutrino detectors on the Earth. We can go and look for those neutrinos. And here I do want to point out that, so this is an exclusion. The thick lines are ice cube and the thick lines are ice cube. The other dashed lines are all different neutrino observatories. And there's a direct detection experiment here, which is PICO, which is the most sensitive spin-dependent dark matter nucleus interaction experiment. Now I want to point out that we're on the elastic scattering, we're constraining the elastic scattering of dark matter with nucleons, and that's because this rate of annihilation is effectively just governed by the capture rate of dark matter coming in and sinking to the center, and that is entirely constrained by the dark matter nucleon elastic scattering cross-section. So the annihilation cross-section doesn't really matter unless it's extremely tiny, which makes this a fair comparison. The other thing that you have to, the only thing that you have to worry about is what does it annihilate into, because depending on the channel, if it's quarks or weak bosons or leptons, you will get different fluxes just because of how the hadronization and decay process works. And so you'll be at an advantage or a disadvantage depending on what the dark matter is actually annihilating into. Oh no, I skipped that slide. So that was all to say that in some regimes, ice cube neutrino detectors are actually better than direct detection experiments at finding certain kinds of dark matter. So I want to move on a little bit to the red giant branch. This is a bit of a detour before the main course. So stars in the main sequence, those are stars that are burning hydrogen in the center, fusing hydrogen into helium, keeping themselves from collapsing. And when they run out of hydrogen, the core collapses. That heats everything up. The helium core collapses, heats everything up. The envelope puffs up because of just Stefan Boltzmann, becomes very red. So we wind up with a red giant. And the tip of the red giant branch, so this core is collapsing. We heard earlier, hydrogen is fusing in a shell around it, slowly heating up the core up to a couple 100 million Kelvin, or 10 keV, at which point helium ignition occurs. And this occurs critically at pretty much the same luminosity for most kind of 0.8 to 1 point something mass stars. So the luminosity of the tip of the red giant branch, where the helium burning turns on, is fairly standard, and it's something that we can go and measure in a population of stars. So there was a paper by Eligio and his student Jose Lopes, very nice paper that looked at that found that capture and annihilation of dark matter inside the core of a red giant star, and I just lazily inflated the sun here, can provide an extra source of heat to your core, and therefore you can reach that helium ignition faster. And what that means, I even copied my animation. What that means is that your tip of the red giant branch, which should be up here, these are just three different, so this is from their paper, this is from three different stellar masses. The tip, which should be up here, will, depending on how much dark matter, you could have a little bit of dark matter or an obscene amount of dark matter, how much dark matter that your star is running into and capturing and annihilating, can give you a tip of the red giant branch that is significantly lower than where you expect it to be. So this is a nice theory paper, but how do we test this? So what I've been doing with a student, and this is still ongoing work, is we say, well, a globular cluster is basically a population of stars that is going around to particular neighborhoods and sampling specific amounts of dark matter. And every globular cluster in, say, the Milky Way galaxies, there's a population of about 10 to the 6 stars. They're about the same age, sort of, kind of. They're low metallicities, which is great. It makes the TRGB, the tip of the red giant branch, a bit more robust. So some of them are in just big sweeping orbits around the outer edges of the Milky Way, and they're not seeing very much dark matter at all. Others are in more kind of radial, or you'll see in a second, weird orbits. And over the course of their dynamical kind of lifetime there, they're sampling the very large densities of dark matter in the center of the Milky Way. So we have a bunch of these globular clusters, a couple of hundred, that are sampling different amounts of dark matter. So in principle, if we can classify them by how much dark matter they encounter in their daily lives, we can see if there's a correlation between the tip of the red giant branch and the amount of dark matter. So what we've done in this, as I said, this is still ongoing work. So this is very preliminary, but we already have some partial results here, and I think they're pretty robust. So we can go and take some Gaia data, figure out what the best, or a range of possible models for the gravitational potential of the Milky Way would be. So Gaia is giving us very precise positions and velocities, initial conditions, and then we evolve those globular clusters backwards, figure out what their trajectory roughly would have looked like over the last maybe giga-year, which is when you would have been in the red giant branch. And then figure out from that how much dark matter they will have encountered over their lifetime. So you can see some of them have these big sweeping orbits around the Milky Way. This is a scale of about 20 kiloparsecs from here to here. Some of them have very interesting trajectories where you can see they might pass through the center more often. And what we get is a nice histogram sort of in log space of how much dark matter on average you're going to run into as a globular cluster. And what's nice is that there's a distribution between, sort of 10 to the minus 3-ish and whatever units these are. These are like, GeV per cubic centimeter, so roughly the local density, up to order 10. But the fact that this spans many orders of magnitude means it's actually quite robust, and we've tested a lot of different ways of modeling, quite robust to the gravitational potential that you choose for your Milky Way. As you might know, modeling the gravitational potential of a galaxy over time is not easy. So then we can take these ingredients and go and look for any correlation between the magnitude of the tip of the red giant branch and the amount of dark matter. And you get something like this. So based on the exposure to dark matter and the magnitude of the tip of the red giant branch, and this up here is dim because astronomers like to put numbers backwards. And what you expect if there's more dark matter is you expect an earlier TRGB, so a lower TRGB on the HR diagram. So you expect some kind of correlation, and the fact that you see no correlation gives you a limit on the dark matter nucleus scattering cross-section, assuming you're annihilating and heating up the core of the star. And so our preliminary limit would have been amazing 10 years ago, so it's about 10 to the minus 35 centimeters squared. But this is using a collection of about 20 globular clusters and being extremely liberal with our errors. So I think there's a lot that we can do to reduce these errors and maybe get some competitive bounds and some bounds that are not centered on the Earth, that are sampling a wider range of the dark matter distribution of the entire galaxy, which is really fun. So what I want to move on to now is a different type of dark matter. So instead of WIMP dark matter, annihilating dark matter, if you have asymmetric dark matter, then it can get captured in your star, and then it's stuck because it doesn't have anything to annihilate to. There's dark matter, there's no anti-dark matter. But here we're talking about a particle that has a very weak interaction cross-section, and therefore a very long mean free path. And it means that if it can scatter in the core, gain kinetic energy because the core is hot, and then travel a long distance, scatter again, lose kinetic energy because it's now hotter than the core, so on average, it's going to transfer heat from the center outwards, and therefore what you have is an extremely efficient heat conductor. So if your mean free path is several thousand kilometers, that's a lot better than a millimeter, which is what your photons are getting you. So because you're transporting heat from the center outwards, you're changing the equation of state, so you're therefore, well, you're changing the pressure and the radial pressure and the radial density profile, and therefore the sound speed. So you're changing the entire structure of the star. You don't have a lot of dark matter to work with, but because it's such an efficient heat conductor, and because something like the sun is very close, we can have a measurable impact on the star. So a little bit more rigorously, this is what's going on. So you're removing heat from the core, so this is the transported energy, removing heat from the core, and depositing it a little bit higher. We're not going very high, so this is like 0.1 solar radii away. And it works best, as I mentioned before, for dark matter that's around somewhere between 4 and 20 GeV, just because that's where you're the most kinematically well matched to protons and helium. Or protons if we're talking about spin-dependent interactions, which I will here just for simplicity. So how do we then go and observe this? Well, what we need to do is have a viable model of dark matter heat capture and heat transport. Then you need to take this, plug it into stellar simulations, evolve them to the present day, match the sun's radius and luminosity, and make sure it's actually, to order 1, the thing that we observe, and compare that model to all the observables that we can find. So because we're changing heat transport, we're changing the temperature profile, just by reducing the temperature very, very slightly in the core, you're changing the neutrino fluxes. If you're Canadian, this is a hilarious joke, by the way. You're changing the neutrino fluxes by an order 1 amount, because so some parts of the PP chain, the boron 8 neutrino flux, is extremely sensitive to tiny variations in temperature. But even more sensitive is helioseismology, where you're looking at the radial and angular eigenmodes of the sun as it oscillates. And because you've changed the sound speed as a function of radius, you've changed the eigenfrequencies of all of the eigenmodes in your helioseismology. There's a possible solution here to the solar composition problem, which I do not have time to talk about. There's also some interesting stuff that can happen in other stars. This was a lot of work on this was done by Jody Casaneas and Eligio. So convective cores in stars that are a little bit more massive than the sun, those will form convective cores. And if you have this extra source of heat transport that's flattening the temperature profile, what you wind up doing is restoring hydrostatic equilibrium locally, and you can erase these convective cores. And with astroseismology, we can now go and look at stars that are not too far away and determine whether or not there's a convective core. So this is just a plot that I find really neat from one of their papers, where if you have no dark matter, you can see that is cut off. It's also cut off on my screen. Oh, no, yeah, I put it here. So the hydrogen fraction is, so this is extremely well mixed in the no dark matter case, but once you add the dark matter, the mixing stops, you lose that boundary, and so your astroseismology, your waves, don't bounce on that boundary anymore, and you can fairly easily see that in the data. So there's already some limits from astroseismology. They're about as uncompetitive as my limits. But it's still pretty impressive that based on looking at a star that's parsecs away from us, we can tell whether or not some dark matter messed up its core. One more interesting thing that we can go and look at from the point of view of a population of stars is the actual lifetime on the main sequence. So this was a really nice paper by Troy Ryan and Zentner and friends. And the site, oh yeah, here it is, the citation is there. And what you're doing as you increase, so this quantity here is the sort of amount of dark matter that you're sampling. So black is a lot and gray here is not. And what we're looking at here is the amount of time on the main sequence, so the delta time on the main sequence with respect to just the no dark matter case. And so if you have a light star, what happens is you're spreading out the temperature profile a bit, and you're bringing a bit more of your star above the temperature required to fuse hydrogen, and therefore you're extending its lifetime by giving it a bigger fuel tank. For heavier stars, you're doing the opposite, where there you have that convective core, and by erasing the convective core, you're not mixing as much hydrogen into the core, and therefore your fuel tank is much lower, and you can, how did I do that? Wow. Okay, this is some keynote. You can sort of squint and see that. I'm almost done with this slide. Yeah, so you can make the lifetime of the star shorter by a factor of 2, which can, potentially affect what a population of stars looks like. But all of this is wrong. Okay, so it's not actually completely wrong. So qualitatively, everything I've just told you is true. But there's a lot of details here that were sort of worked out. They were worked out in the 80s, and nobody really questioned them. But on closer examination, a lot of the techniques behind how we compute heat transport, which is what I'm going to talk about in my remaining N minutes, those details were not quite right. So let me walk you through that. So to actually, there's going to be some equations, but they're friendly. It's okay. To actually model what's going on with this heat transport in the star, what you need to do is you need to solve a Boltzmann equation for the distribution of dark matter, and then figure out what the luminosity, what the heat carried by that population is. So this, it looks like this. That looks nice, right? So D is your differential operator. That's all the derivatives. On the right-hand side, you have your collision term between the dark matter and the nuclei. So dark matter being upscattered, nuclei being, or nuclei depositing or gaining heat, and so on. L here is sort of your mean free path, sort of. And this whole thing winds up being, so we're looking for a steady state, so get rid of time. It's a 6-dimensional integral differential equation, which, okay, it's not, there are no connection coefficients to compute, but it's still hard. And this needs to be solved consistently at each time step because it depends on the structure of the star. So just, I wanted to put up the full thing just to make it look like I do real intellectual work. So what you need, what you can do, you can't solve this generally. You need to approximate, and there are 2 ways of approximating this, either in the very strongly interacting regime or in the very weakly interacting regime. And so this was done back in the 80s, of course, by Raffelt, of course. So Spergel Press 1985 did this, and then Gould and Raffelt did the large cross-section case. And then to see if you're right, you check your answer with a Monte Carlo, and this was last done in 1990. And if you've run something on a computer from 1990, you know the Monte Carlo software was not the best. They did pretty well for the time. So let me explain how this works. So these 2 regimes, so if your interactions are too weak, your dark matter is traveling very, very far, but it's not scattering very often, so your heat transport doesn't wind up being efficient. If the interactions are very strong, you're stuck in place. You're colliding all the time, but you're stuck, so you're not efficiently transferring heat. So there's this optimal regime called the Knudsen peak, where you're traveling just far enough and colliding just frequently enough that your heat transport is optimal. So a little bit more quantitatively, it looks kind of like this, where down here you're in your short mean free path, so stuck regime. Over here you're in your long mean free path, flying around willy-nilly regime. And somewhere in the middle is this transition, which is not analytically tractable at all. But of course, that's where you want to look, because that's where all the interesting stuff happens. So this is all a function of the Knudsen number, which is roughly the mean free path over the scale length of the dark matter in the star, the scale length being roughly the size of the core. So this is the distribution of the cloud of dark matter in the star. So this regime, which was computed in '85 by Spergel and Press, was found to be, so this is formally not right. There's never a regime in which this approximation is formally correct. And it's off by a factor of 2 in the regime in which it applies. And this one needs some kind of ad hoc radial correction because all of the approximations basically break down in the core, which is the important part. So I'm going to go through this very quickly, but just because I think it's interesting. So the isothermal regime, everything looks like a Maxwell-Boltzmann, and you sort of, which is the solution to a collisionless system. And you say, well, the dark matter, it's in a cloud, that's approximately at a single average temperature. And then the heat transport that you get, it just looks like two heat baths that are in touch. So it depends on the difference in temperature between this isothermal cloud of dark matter and the local temperature of the star. So it looks like regular primary school thermodynamics. But if you go and simulate this, it turns out that the actual dark matter temperature is not the same temperature as the nuclei, and it's not the isothermal assumption. It's somewhere in between. So of course, this assumption is going to break down. The second way of computing this, the LTE, local thermal equilibrium regime, that's where you say, well, everything is in thermal equilibrium locally with the nuclei, but there's a bit of a dipole, and that dipole is what's responsible for the transfer of heat from one place to another. So what you do is you expand your Boltzmann equation in a series in the mean free path, and here the mean free path is very small, and then you keep the first order term in this, and then you decompose it into spherical harmonics, and then you keep only the dipole, and you wind up just approximating this as this little dipole contribution everywhere in the star. And formally, this is extremely correct, and it winds up with a very nice form of the dark matter distribution, which just depends on one parameter alpha that you can calculate, and the gradient of the temperature. And the luminosity, the amount of heat transferred, depends just on the gradient of the temperature. So again, this is more like high school thermodynamics, which is fantastic. But if you look at the core, let me look here. The core is not a dipole, and the core of the energy is going in every direction, right? So if you assume that everything is pointed in the same direction, you're going to vastly overestimate the amount of heat that you think you're transferring. So what we do is we take the Monte Carlo results from 1990, and we add a sort of an ad hoc suppression. We multiply it by a small number at 0, so there's a sort of cubic function near the core to suppress the heat transport and try to match what those Monte Carlo simulations gave. So ever since, I don't know, mid-2000s, when people got reinterested in this, the correct approach has been seen as that latter calculation, so the large thermal equilibrium calculation, or the local thermal equilibrium. We need to do that radial suppression, but we also need to account for the fact that the approximation of short mean free path breaks down. So there's another correction on top of that you need to add. And so this is effectively what we're doing. We're taking this correct approach, applying these corrections, and then we're going into the short, so the small cross-section, large mean free path regime, which is currently what's allowed by direct detection experiments. And there's another problem with this, and that is these, if you try to implement them into stellar simulations, are extremely numerically unstable. So this is a PRL article from Fabio Iocco and friends back in 2012. You can see these just giant numerical instabilities from the evolution of stars. So this is an HR diagram. And these are evolutionary tracks of stars. I managed to reproduce that. The Canadian Journal of Modern Art is not a real thing. That's a joke. But as you can see, it's very difficult to get these things not to be unstable. So the solution to figure all of this out is to solve the equation exactly. And the only way I know how to do that is via Monte Carlo. So we stick a particle in a star, and then we let it random walk its way around. And just by ergodicity, we'll figure out what the thermal distribution, what the distribution function is based on the history of that particle. So there you just need to, you specify a mass of your dark matter, you specify an interaction cross-section, you specify a background, what is the star, what's its composition, temperature, gradient, pressure, pressure doesn't matter, density profile. And you specify the microphysics of what happens in the collision between the dark matter and the nucleus. Is there a long-range force? Is there some kind of weak-like force in the kinematics of the collision itself? This is a technical slide that I'm going to skip because I'm already low on time. So thousands of CPU hours later, this is Monte Carlo, we come up with these plots. So these, just focus on these ones. So this is heat removed. These are data from the Monte Carlo. Heat removed from the core, deposited above the core. And as you can see, so the Goulden-Raffelt, the LTE solution, works very well in the LTE regime. Spergel Press does not, because it's not meant for that regime. For small cross-sections, Goulden-Raffelt still works because of that suppression. And the Spergel Press looks very good, but it's off by a factor of 2, which we've known since 1990. Okay, that's not bad, but it's not great either. If you have different types of interactions, things get bad very quickly. Where, again, you have the data, which are green, and the analytic predictions, which are the lines, and you can see that nothing works. Right? So if you have a non-constant cross-section, none of this is going to give you anything reasonable, which we didn't know until someone simulated it. So this is a problem. But what do we know? We know that the Spergel Press, so the isothermal solution, gives a much better shape of the luminosity. It's just off by a constant factor than the supposedly correct calculation. The approximation, the LTE approximation in the supposedly correct solution also doesn't make any sense anymore because we're in a regime of cross-sections that is basically direct detection experiments tell us that we need to be in the isothermal regime. We need to be very far away from the LTE regime. So we're off by a factor of 2, but that doesn't seem like a big problem. So what we're going to do is we're going to correct the Spergel Press regime, the Spergel Press approximation, for small k, so see what happens if we try to empirically include the fact that your mean free path might be smaller than what makes sense in the approximation, and then sort of empirically calculate or calibrate it from the Monte Carlo simulations itself to give us a formalism that we can go and put back into stellar simulations and figure out what the actual observables are going to be. So it turns out to be very simple. We take the luminosity from the Spergel Press calculation, we adapt it by this factor, this f of k, where k is the Knudsen number, k naught is determined by the simulations, this overall scaling factor is determined by the simulations. It's approximately, but not exactly, a half. We're still trying to figure out why that is, or why that number is there. And so this blue curve is the prediction from our updated formalism. And as you can see, it looks pretty cool. It looks pretty nice. So these are just different types. So these are different cross-sections from strong interactions to weak interactions up here. And this is a lot of graphs, but these are different types of interactions. So these are interactions that go with the velocity or go with the exchange momentum. And the entire takeaway is, look, the blue curve matches the simulations very, very well. And so we're pretty confident now that we have a formalism that we can go and put into stellar simulations, and it should give us results that are reasonable and believable. And you might ask, like, well, how robust is this to weirdness? So this is the maximum luminosity predicted. So like I said, we fixed that k naught, and the beta is the same for every model. The overall scaling is the same for every model. And these are 7 different types of dark matter nucleus interaction. The curve is the prediction, and the data points are the Monte Carlo data. So that's for a realistic solar model. The only thing that's not realistic here is the gravitational potential, and we're updating that now. Here's an idealized model in which the sun has a radius of 2.4 meters. The density is 1 kilogram per cubic meter. The temperature at the center is 1 Kelvin, and the dark matter mass is 1 kilogram. And it looks super weird, but it's still a pretty good match. So that sort of convinced us that this is relatively robust. So now we're ready to go and actually take these results, stick them back into stellar simulations, stellar evolution simulations, evolve a star billions of years, look for observables, and try to figure out what main sequence stars are actually telling us about asymmetric dark matter. So just to summarize, dark matter nucleon couplings, if you can find them in the lab, you can find them in stars. And there's loads of very interesting phenomenology, and we're kind of in an arms race right now with the underground lab people. We're kind of probing the same regime, same kind of cross-sections. We're doing a bit better in the spin-dependent case for some types of models. But we're only now really starting to understand how this sort of dark matter particle can affect main sequence stars. And specifically, what kind of dark matter particle is having what kind of effect. So there's loads of ongoing work in my group. We're trying to tackle the solar composition problem as well. We're looking at electrons, dark matter electron interactions as well. Different stars, different So spin-independent interactions, so interactions with other nuclei, because this was all just spin-dependent. But I think this is also complementary to direct detection in that we're sampling, in principle, the entire stellar population of the Milky Way. And we've learned something about non-local heat transport along the way, which I think is neat. I don't know what we've learned yet, but we've learned something. So thank you.
Questions? Thanks for the talk.
Thank you for your very interesting talk, but I am pretty sure that we are aware that all those effects, or more of them, you were discussing can be also caused by modified gravity. Like, for example, heat transport. I mean, I studied only convection processes, but I am sure that other processes will also be affected, like the different evolution, like shorter time on mass cycles or longer. I mean, it depends on the theory and so on, but almost everything here you were discussing, which is fascinating, and you are like really doing, I mean, like serious stuff, because I am considering toy models because of the difficulties of the equations and analytically. So this is fantastic, but I expect that everything you were discussing, I mean, in modified gravity, you will have a very similar effects.
Probably. Yeah, I agree. So there's two scenarios, right? Either we don't see anything and then we rule out two things, or say we do see something weird, then we need to figure out what we've discovered. Yeah, then we really need to understand the details correctly to figure out if there's an observable difference between the dark matter effect and the modified gravity effect. Yeah, I agree that yeah, we don't want to be too narrow in our focus.
Yeah, because I have an impression sometimes that people from dark matter are only like thinking like, oh, I find something, so for sure it must be dark matter, but it's not so.
No, I wouldn't say for sure it must be dark matter, but it would.
I have also a lot of questions, but maybe later we can also discuss. Thank you.
Thanks, Aaron. So in your slide number 13, where you show this tip of the red giant thing.
13.
Yeah. The shift of the tip with no dark matter and with more dark matter is like in the x-axis is like 3.5 to 3.6. So with this very small delta t or the difference in the shift, how do you expect or why do you expect such magnification in your observables that you show in your following?
I mean the temperature. I don't think you would see. This is the log of the temperature. But I don't think you would be. A lot of stuff can affect the x-axis. There's like mass loss in the envelope. There's also all sorts of confounding things. What is really important is this axis here. It's the magnitude, because it's that's shifting down, and no matter what you do, so no matter what I have to be a bit careful. It looks like, independent of how you're modeling your red giants, the delta here seems like it's fairly the same. And I know you guys did, maybe Eligio might be able to answer that. I've done not these simulations, but a similar new physics thing. And the difference here is what you're really looking for. Do you want to add something?
Yes, thank you.
Okay, thank you. Nice talk. I would like to ask a question. In answer to the 2 points, one is the lady there, you made a very interesting comment. I agree with you about modified gravity and dark matter. I think you can say for sure with do not work. When it works, then you say, okay, maybe it could be, but that's it. I mean, it's very difficult, and it happens in anything that is indirectly. It's very difficult to make a claim if you find a match, and then you say, oh, I find a match and therefore works. No, it's just a clue that eventually the solution is there. I agree with that. But if you refuse it, maybe it's a good, you are in a good position to say very likely that you can reject this model of particles or this modified gravity and so on. Relatively to this point about the tips. Now, the nice thing about the tips of the red giant branch, actually my students not here could also help on that. But on that is important. Oh, you are there, Joe. Maybe you want to comment on that too. What is important is this has been actually being very interesting because you can see stars very far away, and it's like a way to put very important things in cosmological terms. And the interesting thing is not very sensitive to the physics of the star. Actually, for a small range of masses, and you have a lot of stars that are they are very bright, as you can see, and for, I don't know, between maybe 1.2 and 0.9, you have lots of stars. What really defines the tip at first order is just the helium flash, as you explained well, is when basically you start to burn helium. And because the envelope actually is not very important. And because of this single effect, that's true, the other effects also play, but they're second nature. And therefore, when you introduce the dark matter in this kind of effect, when you have this effect, it's quite large. This effect is quite large compared to other things. If you compare, for instance, for the standard physics that you could expect, oh, if I slice this and that on the model, this will affect not very much. Compared, for instance, that you have in the solar, abundance problem. It's more competitive. And this is why it is a little robust, and is why this has been used in cosmology as a way to trace, because you can see far away, but also because it's a well-established result. Now my question is, have you looked to the form factors on all these kind of analyses? I know it's a very tough thing, but I'd like to have your opinion.
Oh, in the
on
heat
that.
transport, the nuclear form factors.
Yeah, the nuclear, because the interesting thing is you can look at the same thing for the detectors and also for
So I've done a lot of that in the capture rates because it's slightly easier. For scattering, we haven't looked at nuclear form factors. I don't think it would be a huge problem because those are only really important if you have high enough momenta to sort of get a de Broglie wavelength smaller than the nucleus. And the scattering inside the star is mostly very low momentum inside this kind of star. Maybe if you're in a neutron star, then I'm not going to say anything. Yeah.
In the Monte Carlo simulation you were doing, is back reaction something you have to think about? Like, as the dark matter warms up and moves around, does it affect how the rest of the dark matter warms up and moves around? Yeah,
so we're doing this in 2 steps, and it's because it's impossible. Well, I won't say impossible. It's impossible to do this fully self-consistently, just because you need a full Monte Carlo simulation for a single time snapshot. But the equilibration time of your dark matter is way faster than the evolutionary time scale, or like characteristic time of your star. So the reaction of the dark matter is going to be faster. So in that sense, it is reasonable to just see what the equilibrium distribution is, and then maybe try to test it with a different stellar model to see, does my prediction for what happened at that time step match what a Monte Carlo is there? But the full self-consistent, treat the back reaction instantaneously, that's not really necessary unless like you're in a supernova or something very fast.
Any other question?
This may be a silly question. In terms of density, I'm guessing there are many orders of magnitude difference between the dark matter density and just the ordinary matter density. But is this large enough to make strong interactions between dark matter particles irrelevant to the scenario? Can you have isothermal dark matter distribution because they come into equilibrium through strong interactions amongst themselves and affect the scenario?
Yeah, so that's a good question. So the amount of dark matter that you wind up accumulating in the sun is like 10 to the minus 10 solar masses at most, right? It's very small, but you can get enhancements in the capture due to self interactions, sizable enhancements, and there are loads of papers about that. Self interactions in the context of conduction. That's really interesting, and I don't know that anyone has really looked into it. I mean, given that you can get enough annihilation in annihilating scenarios, I would think that if you have no annihilation but elastic scattering, you can get at least some amount that'll give you some kind of equilibration. Yeah. So the answer is I think that's worth looking at. I don't know how to do it very easily. Because, yeah, in the Monte Carlo, you only have one dark matter particle.
The extreme limit may be easy, right? You know, you just go to the limit where the dark matter is isothermal and it's just maintaining its temperature because it's in thermal equilibrium with itself. The cross sections are large enough.
Yeah, that's true. Although I always worry about how true that assumption actually is based on what we've seen, right? And will it make a difference in the end in the transported heat? Yeah, it'll be more true in that case than in the Spergel Press assumption of isothermal distributions. Yeah. In step 2, yeah.
Not any more questions? Then, thanks again for your talk.
Thank you.